Yeah, so we are now at the final chapter. It's about linearization coefficients. So the linearization coefficients are important uh, quantity in the following sense. So as usual, let's suppose that we have a monic OPS with linear functional L. So they are orthogonal with respect to this linear functional, and so they are in particular they form a basis of the polynomial space, but we have polynomials, so we can multiply two polynomials. So we can multiply p say m and pn x. In the orthogonal polynomial sequence, we can just choose two polynomials and then we can multiply them. It's a polynomial, of course, so we should be able to express this as a linear combination of the polynomials themselves. So there is a unique expansion in this way. So PL of x. And there is a coefficient which I'll temporarily write this way. So we can always find, at least there is always constant like this, the coefficient like this. But question is, how can we compute this? The process of this is called linearization because we have non-linear term here, like multiplication of two polynomials, but we make it linear like this. So it's called the linearization problem. And now we have this linear functional and orthogonality. We can compute this quite easily, at least in the form of linear functional. We multiply PL both sides and then take the linear functional, and then we will only get this. The other terms will disappear. So multiply PL x and take the linear functional L, then we will get L of PM, maybe L, let me just omit x, equals, we have only this term surviving, L squared. The other terms will all disappear by the orthogonality of this. That means this coefficient in the linearization is L of, this is n. But we know that this is the product of lambda 1 up to lambda L. These are the three-term recurrence coefficients. So in order to compute this, it is enough to find this quantity. So this is called a linearization for that reason. So definition, a linearization coefficient is something like this. But more generally, we multiply more than 3. So in general, we're gonna call a quantity like this a linearization coefficient. Okay. If k equals 2, we multiply two polynomials. It's just orthogonality. So the goal in this chapter is to find combinatorial interpretation for the linearization coefficient, but not in the general case, but for some special cases. We'll find, our goal in this chapter is to find combinatorial models for the linearization coefficient for classical orthogonal polynomials like Hermite, Charlier, and Laguerre, like that. We will consider these three classical orthogonal polynomials. But the idea, let me briefly tell you the idea. In order to find a combinatorial interpretation, we need to give some combinatorial meaning. But for every polynomial, we have a combinatorial meaning. So first, maybe I can step by step. First, find a combinatorial model for the polynomials. But we know how to do this. There's a Hubbard path, for instance. But we will be considering some special cases, so Hubbard tiling is not enough. We will give some more intuition into the combinatorial model. And then find the combinatorial model for the moment, mu n. But mu n is x to the n, right? But we already know this using Matchkin path. But again, for the special case, we will convert this Matchkin path into something else, like matching, set partitions, permutations, like that. So now, suppose that we have a combinatorial model for this and a combinatorial for this. Then, third step is L of P(n)(1) dot 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 P and K. Using the combinatorial model, we can expand this as a combinatorial generating function and etc. So we have a k tuple of combinatorial models. And then they have some x in it. If you collect all the x's and then applying L to it gives us this moment, which also we have a combinatorial model. So we have, at the end, we have everything explained completely combinatorial, and there are many cancellations. And the next step is to find the sign reversing involution and get only the terms that we want. At the end, we will get very nice combinatorial models for all of these. They all have some kind of similar structures, but somewhat different. And proof is also quite interesting. So, yeah. I think this is a very interesting chapter. So that's basically the idea. Combinatorial interpretation. So just vague idea. So we'll have to look at some specific examples. So first, Hermite polynomial. So this is our favorite polynomials in the sense that they are simple enough and also have nice structures. But we will use rescaled Hermite polynomials. So h and tilde. So they satisfy this recurrence relation. After rescaling, we get a nice recurrence like this. And as usual, the zero term will be 1, minus 1 index give us a 0, like that. So we have a recurrence like this. And we know that the nth moment, mu n, is x to the n. And using the Vienna's combinatorial model, this is the number of, or weight sum of Dick path. But we know we translate the Dick path labeled or Hermite histories into complete matching. So this is the number of perfect matchings. On n. So in particular, if n is odd, then it's going to be 0. So we need some definitions or notation. So M sub n is the set of all matchings, not necessarily perfect. And for, by the way, this is M, right? M, not mu. And for a matching, say tau, E of tau is the number of edges. So matching is an object consisting of edges and fixed points or singletons. And fix is the number of fixed points. So for instance, if we have a matching like this, if tau is this, what is the E of tau? number of edges 2, fixed number of fixed points 1, 2, 3, like that. Okay. And we first need to find the combinatorial meaning to the Hermite polynomials, rescaled Hermite polynomials. There is a simple model like this. So generating function for all matchings where we multiply this -1 to every edge and x for every fixed point. So this is our combinatorial model. Proof is really easy by induction. Because, you know, imagine that you have a matching of size n+1. There are two possibilities. This is a singleton, or this is connected to something. But if you want to connect this to one of these, there are n possibilities, just like this. And the minus gives us the sign here. And if this is a singleton, then it will contribute x. So that's basically the proof. So I'm gonna just omit the details. So for instance, maybe I can just give you an example. H2, say H3, 3 star x. We have consider all matchings. No edges, one edge, like that. And every x, a fixed point has weight x, like this. And every edge has weight -1. So this is going to be x cubed minus 3x because of these four matchings. Okay. Now, this definition will be used quite often in this chapter. So let's say n1 and k are fixed integers, all non-negative, and let their sum be n. And for S, J of sub S is the set of all integers I, such that so this is a formal way to say that we have integers 1 up to n. I'm going to divide this n1, n2 like this, nk. And the set of elements here is going to be j1, set of elements here is j2, etc. That's what I define this. Okay, just a formal way to define this partition. But they could be of size 0. And so n is the disjoint union of these sets. This means cup means disjoint union. Okay, now let tau be a matching. And we say that on edge is homogeneous if both I and j is the same set for some s. Okay, so like this edge is homogeneous, but otherwise inhomogeneous. So homogeneous means an edge coming from the same j set, and inhomogeneous means you take two different j set and then take elements from them. Like homogeneous, inhomogeneous. Okay. And we say that tau is homogeneous if every edge is homogeneous. But actually, more important thing is inhomogeneous. If every edge is inhomogeneous, okay? So matching is homogeneous, that means every edge is homogeneous, and matching is inhomogeneous if every edge is inhomogeneous. There is something in between, but we don't really care. Okay, and finally, IPM of N1 dot 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 NK is the set of all inhomogeneous perfect matchings. On this set N, where we divided N into like this. So a typical example of an inhomogeneous perfect matching looks like this. It's going to be a perfect matching, so we must have so this must be connected to something outside. An inhomogeneous matching looks like this, for example. So you have to connect something that's not in the same group. So this is not homogeneous. All right, now we have all the necessary definitions. So now I can state the theorem of the linearization of the Hermite polynomials. So the linearization coefficient of the Hermite, I'm going to omit x, is the cardinality of inhomogeneous perfect matchings. It's a very simple description. That means this is basically the number of ways to connect dots like this. That's all. So in particular, it is positive. It is a positive integer, or non-negative integer at least, which is not clear from this definition, because they have some minus signs. For instance, they have minus signs here. So it's not clear at all why this is true. This is positive. But the thing is, it's always non-negative, and it really counts something like this. So linearization coefficient is very often looks like this, inhomogeneous object. So we will see later that for Charlier and Laguerre polynomials, we have similar situations. We have it counts like inhomogeneous set partitions, it counts inhomogeneous permutations like that, but this is the first thing. Okay, let's prove this. Okay, proof. First, we're gonna write down the formula for the left-hand side. We know a combinatorial model for this, everything. So just replace this by the generating function. So I'm gonna write this way, tau 1 dot 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 tau k. So we have tau 1 for this polynomial, tau 2 for this polynomial, etc. There's like a tuple, mn1 cross dot dot dot. This is nothing but you select one matching from this, one matching from this, etc. And we have to multiply I from 1 to k. The sign is, the weight is -1 to the number of edges for every matching, x to the fixed point. This is nothing but replacing every Hermite polynomial by this lemma over here. We didn't do anything serious. And now we use the fact of the linearization, the linear functional. So tau 1. Let me omit the set. So this is by the linearity. Let me just write it this way. And now we have L of x fix tau 1 plus dot 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 fix tau k. I just collected, I just used the linearity of the linear function. So, but now you see, this is nothing but a moment. It's like mu sub this. So this means number of perfect matchings of size and fixed tau 1 fixed tau k. Is that right? So to understand this, let's just see an example, just vague. I'm not going to give you a precise example, but let's imagine that we have something like this. We have situation like this. So this is like n1, n2 dots. So every block we have to find a matching. So it's like this, or so one edge here, maybe two edge, but let me just put one edge. So 1, 2, 3, 4. Okay, this looks very special, but let me just choose edges like this. Now they have weight -1, every edge, but for the remaining fixed points, they contribute x. So x to the fourth. For x to the fourth, if you multiply, apply the linear functional, we will have to compute x to the 4. But this is the number of ways, the number of perfect matchings of size 4. That means we have to connect. This is a number of ways to connect the dots, so that we have a perfect matching. Let me use red. So it is something like that. So this is basically a number of generating function for, okay, maybe I can explain the definition later, and let me write down and explain what it means. So tau is basically union of all taus. Just you take all the unions of this, so like only the black edges. And pi is the perfect matchings on the fixed points. So it's the red edges in this example. So black edges. Okay? So x is a set of all pairs, tau and pi, that looks like this. And tau, every element here, this must be homogeneous. And this must be, it can be homogeneous or non-homogeneous, doesn't matter. Every edge here is homogeneous. Tau, homogeneous. But no restriction on pi. And then what is the sign? The sign is the number of black edges, but that's basically the number of edges in tau. So we have a configuration like this. Just imagine these are fixed. Imagine all possible configurations like this, right? And then our goal is to cancel things with minus signs. But how can we do that? But the idea is quite simple. If you can just change the color, then it will change the sign, because only black edge has minus sign, red has plus. So for instance, if you can replace this by red, then it will be cancelled. But you cannot always change colors. For instance, you cannot change this into a black edge, because black is always homogeneous. So as long as you have a homogeneous edge, changing the color is always possible. So that's the idea. So let's find the sign reversing evolution. So phi. So tau So the idea is if maybe case 1, let me write 1, tau, or there is no homogeneous edges. Both tau and pi. Then we define this to be a fixed point. But how can this happen? Tau is homogeneous. If it has an edge, it must be homogeneous. So that means this is actually a fixed point only. So meaning nothing. If tau has nothing, and so everything is a fixed point. This must connect all of them. So this must be an element in inhomogeneous perfect matching, because otherwise it's not going to be in this case. So this is a fixed point, a nice fixed point for us. Second, there is at least one homogeneous edge. And the idea in this case, like there could be many, so we have to find a way to select a specific homogeneous edge. So let I, j be the homogeneous edge with smallest j, say. If there are many, choose the homogeneous edge so that j is the smallest. J cannot be shared by other homogeneous edges, so it's going to be unique. Then, because it's homogeneous, we can change the color. So change the color of. That means, in other words, move this edge from tau to pi or vice versa, depending on whether it is. So maybe I can give you an example. But the claim is this is a sign reversing involution. Sign reversing involution. Actually, it's quite easy if you think about it. Yeah, so proof. Easy if you understand things. But let me just give you an example. That'll be, hopefully that'll be enough. Okay. So here we have n1 equals 5, n2 equals 4, n3 equals 1. So we have edges like this, and red edges like this. Okay. So only black edges have minus signs. And in this case, there are some homogeneous edges, so we can cancel, or we find what is the smallest, or what is the leftmost, or the homogeneous edge with smallest j. There are 1, 2, 3 homogeneous edges, but this has the smallest j. So we will change the color of this, then we get this. This is obviously an involution, because if you are at a situation like this, this is still the smallest homogeneous edge with smallest j. So you will change this color, you will get this back. It changes the color of one edge, so it changes the sign. So that's it. So it's a sign reversing involution with fixed point exactly IPM. That proves this with a sign reversing involution. Okay. There's the proof. So very nice proof. And in particular, a corollary, maybe I can write down the corollary here without this. Corollary. hm tilde hn tilde equals delta mn n factorial. Why is that? We have m, n. This, by the theorem, this is the number of homogeneous matching, perfect matchings on this set. That means you cannot connect things among them and things among them. So you will have to connect them like this. But it must be a perfect matching. So it's a bijection. It gives us bijection between this set and this set. A bijection exists only if they are equal. But if they are equal, the bijection is the number of permutations, so it's n factorial. So that proves this orthogonality immediately. It's a nice theorem. Actually, this is the first time I encountered the beautiful combinatorics of orthogonal polynomials, like many years ago when I was a graduate student. There was a postdoc at my university. His name was Dan Drake, and he explained this idea, the proof of this orthogonality of the Hermite polynomials, and I was very fascinated by this idea. So I was, oh, it's cool. So but that was a long time ago. Okay, so that's the Hermite case. This is the simplest and nicest case. And if you go further, it gets somewhat more complicated, but the idea is similar. Charlier polynomials. And recall that we define the Charlier polynomials in this way. Minus a n c n minus 1 x a, but just for simplicity, let's consider cn with a equals 1. So this on a equals 1 case. I will cover only at the a special case a equals 1. The same idea works in the general A. So I will just, for the sake of brevity, I'm going to use this. So then let me rewrite the recurrence. So x minus n minus 1, a equals 1 now. N, c n minus 1x. So this is, so Bn equals n plus 1. Lambda n equals n. So the moment in this case, we computed that this is the number of set partitions before. So I'm going to use that fact. The set partition, set of all set partitions of n, okay? Using the Vienna-Motzkin path model, we proved that this is true. Okay, so we will use that fact. And we need some definitions in this case. A little bit of definition. Decorated permutation is basically the permutation with a choice for every cycle, in which every cycle may or may not be decorated. So it's like you have a permutation with a disjoint union of cycles, cycle decomposition. For each cycle, we have two choices. That's decorated. It's like decorating the cycle or not. So, but what we really need is not just decorated, but properly decorated. Properly decorated permutation is, first of all, the decorated permutation such that every long cycle is decorated. Long By long, I mean a cycle of length at least 2. Every cycle of length greater than or equal to 2 is decorated. So decorated, you should think of this as like cycle. I don't know, like example, maybe 1, 2, 4, 3, 5. So we have some decorations. Let's say I decorated with star here, and star like that, maybe one more, 7. This is a decorated cycle, a decorated permutation, or it is not a properly decorated permutation because this cycle is not decorated. If you want properly decorated, you have to decorate every cycle of length at least 2. But for cycle of length 1, we have 2 choices. So that means properly decorated means you have only 2 choices for cycle of length 1. For other cycles, you don't have any choice, but you have to decorate them. Yeah. That's some notation. And Dn is the set of all decorated permutations on n. And Pd properly decorated permutations on n. Okay, I'm going to use these 2 notation. Oh, and one more. dc is the number of decorated cycles in pi, of course. So, right, now we can write down the combinatorial model for the Hermite polynomials lemma. Cn, Hermite polynomials, is the generating function for properly decorated permutations with the weight like this. Okay? We have some signs, which I write somewhat separately with -1 to the n and -x to the dc pi. Proof. Yeah, you can imagine, just like Hermite polynomials, we have a 3-term recurrence, and you have combinatorial model. Proof should be straightforward, right? Just like Hermite. But in this case, we need more work. It's less trivial than Hermite, because Hermite, it was really trivial. You just connect n+1 to something that gives exactly the term in the 3-term recurrence. But in this case, we need some cancellation in the 3-term recurrence. So we need some extra work. But we should be able to do that. So let f and x be the right-hand side. And then we're going to show that this is equal to this by induction. We will show Cn equals Fn by induction on n. N equals 0 is true. N equals 0, 1 is true. You can just check it. Just a simple check. And suppose it's true for all k less than or equal to n. And then we're going to prove that it's also true for k equals n+1. So to prove that it's n+1 is sufficient to show Fn n+1 satisfies the same recurrence, right? Because then this is a Cn, this is Cn-1. By the recurrence for the Cn, this is Cn+1, so we get the recurrence. So we will prove that this. So that now everything is combinatorial, so we can prove this combinatorially by finding some sign reverse involution. But it's a little more complicated, so we have to be careful. So the right hand side here, let me rewrite in this way: x fn minus fn minus n times fn minus n times fms. I just rewrote them this way. So each term will correspond to something. This, my claim is, this is equal to minus 1 to the n minus pi a1. I'm going to define a1 later. Minus a2 dc pi minus the same thing with a3 plus a4. Okay, the same, I'm writing the same thing. Now I have to define a1, a2, a3, a4. So a1 first, a1 okay, maybe I can just write it this way, where a1 is a set of permutations pi. It must be a permutation in decorated permutation with this condition: pi is sigma n plus 1 star, where sigma is properly decorated. Okay, so why? Let me explain why this is. So this is supposed to count this. So imagine that we construct some decorated permutation with n plus 1 elements, 1 up to n plus 1. So imagine n plus 1. So n plus 1 must be something, right? Must be, it may form a single cycle, or it may be connected to something. So in this case, I'm going to consider the case that this is single cycle decorated. In that case, we're going to get this, because decorated cycle gives us a sign, minus sign, and also x here. So if you have n plus 1, this will contribute to x and minus sign, and then you get all this. That's basically the idea. And what about a2? Same thing, same pi, where pi is now a sigma n plus 1 without decoration. Because here, we don't have any decoration, so we don't have any x. And we don't have any minus signs, but we have minus here, because here, this has n plus 1 over here. This n plus 1 and this, if you combine them, you get that. That's the, you have to check by yourself, but this is a simple check. And a3 is pi, where pi is, let me explain this way. N plus 1 pi is sigma with n plus 1 inserted after some integer. So see, this is a permutation, so it's cycle. It has some cycle structure. I'm going to add n plus 1 somewhere after this. Not at the front, but something after. Okay? That's what a3 means. And that gives us this, because there are n ways to insert n plus 1. There are n integers. You can insert this after any of these n integers. And the sign also comes from the fact that the size here is n plus 1, the size here is n. And finally, a4 is this. Pi is, let me write this way, pi prime I n plus 1, where pi is PD pi prime is exactly pi with every j increased by 1. This is something like, I'm going to create a new cycle of length 2 with I n plus 1, but obviously this will contain I because it's a permutation. So I'm going to increase all the integers greater than or equal to I by 1 so that now it has I missing. So that if you include them, this is going to permutation on n plus 1. This is just a way to construct. Because, oh, sorry, this must be n minus 1. We have n minus 1 entries. We have 2 more entries, so it's going to be n plus 1 in total. So this is from f n minus 1. Okay. It may not be obvious at the moment, but if you think about it, it's not difficult. It's only if you understand the definition, it should be straightforward to check. Okay, but here, not everything is properly decorated. For instance, this is okay. Everything is properly decorated because this is already properly decorated. Cycle of length 1, we have all possible choices. Properly decorated or not. So these two are okay. They are properly decorated. What about A4? This is not properly decorated because it's a cycle of length 2 not decorated. So this is always not properly decorated. But here we have sometimes you have properly decorated, sometimes not properly decorated. But when does an element when is this properly decorated and when it is not properly decorated? So in A3, we have properly decorated. This is properly decorated. We have to insert n plus 1 somewhere. If this is already properly decorated, this is okay. If it's not properly decorated, if you insert this, it's not going to be okay. But when can this have a non-decorated cycle? Cycle of length 1. So pi is not properly decorated. If and only if pi is inserted and is inserted to a single cycle, a cycle of length 1 that is not decorated. That's the only possibility, because if you insert something that was already decorated, then this is okay. But if you have something that's not decorated, but that only possibility is cycle of length 1, because this is already properly decorated. So this is not properly decorated if and only if this. But this will cancel exactly with A4. So we have all the cancellation, and we are left with all permutations, properly decorated permutations of size n plus 1. That's the, I'm not explaining in full details, but that's basically the idea. Okay, if you think about it, so we are left with exactly properly decorated permutations. So it proves that with a correct sign, it proves that this is equal to this. Okay? Now let's move on. And before stating the theorem, I'm gonna need one more definition, but this should be familiar with you. Again, N1, Nk fixed. A cycle is homogeneous if all elements are in the same set Js for some S. And as you know, S is the segment of the set 1 up to n, right? And inhomogeneous, of course, a cycle is inhomogeneous if every edge, every arrow, say, it, connects two distinct, two elements from, say, JR, JS. So like this, if you have a cycle like this, every edge or every arc is homogeneous, inhomogeneous, or in other words, every arc, arrow or arc is inhomogeneous. It may have some two elements in the same set, but they are not going to be adjacent. Okay. Okay, now I can state the theorem. Let's see. Theorem. L of Cn1 dot 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 Cnn Nk equals oh yeah, I forgot to define one thing, but I think I'll have to do this here. You can imagine this. N1 dot 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 Nk is the set of inhomogeneous match set partitions. Okay, but by inhomogeneous I mean okay, no singleton, every edge is homogeneous, inhomogeneous. So in typical example is like set partition, so it connects things like that. So it is not allowed you have a singleton like this. This is not allowed. This is okay, but this is not okay. Okay? So inhomogeneous set partition looks like this. Okay? And the theorem is yeah, let me just erase this. We don't need this. The number of inhomogeneous set partitions, just like you can imagine, just like this is the best thing we can imagine, right? So let's see if you can prove this. Right, the idea is similar. We write down the left-hand side equals, first of all, I'm going to pull out all the -1 to the n. You know, we have -1 to the n1, -1 to the nk, etc. Their sum is going to be n. So n equals n1. We don't need that in the assumption, but I'm going to use this. And after collecting all the minuses, now we have this summation tau1 dot 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 tau k in the set pi n1 dot 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 pi nk, and product I from 1 to k minus x to the number of decorated cycles in pi tau I. Right? You know, I collected all the minus signs here at front so that we get only decorated cycles like that. So they're all collected. Then again, we can move this over here, and then maybe I can -1 to the n tau1 dot 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 tau k. So -1 to the decorated cycles and L of x to the decorated cycles like this. But again, this is just a moment. What is this? Number of set partitions. So the idea is, just imagine the situation. We have something like that. So here we make permutation. So it must be a homogeneous cycles. It must be, because we can only use things over here. This is for Cn1, right? So when you do that, you have some bunch of cycles here. Let me just write it that way. And some fixed point. It's a properly decorated. So you have some decorated cycles, and maybe I should write it bigger. You have, but whenever you have a cycle like bigger than length 1, it must be decorated. So it's decorated. Let me write decorate this way. So for one cycle, may be decorated, but may not be decorated. So a typical situation looks like this. Decorated, non-decorated, other. So you have something like that. Now, just consider all the decorated cycles as a single element, single dot. And then we find set partition. We just make a set partition out of this. So it's like, you can make a set partition like this, or this, or that. This is our configuration now, okay? That is the idea. So let me write it in more precise fashion. Okay, so X is the set of collections, pi. So a set of configurations like this. So X is basically, I'm going to try to encode this as a properly defined terminology. So it's like a set of collections such that, first, every BI is a collection of cycles, homogeneous cycles. C, let's say T, non-empty set. Let me homogeneous cycles. And second, if you combine all of them, Cji, everything, if you collect everything, these are the cycles. So one, say I up to R, J from 1 to, basically what I mean is we collect all the cycles, all the cycle structures. So this is a set of cycles. You collect all the cycles. You take the union of all of them. This, and then think of this as just a set. And this is a partition of a subset. Say A of n. Because here we don't collect all the numbers. Some things are missing. And the missing parts are exactly those non-decorated cycles. So as a set, this as a set. And third, no, that's it. So the idea is the set X is like you have a bunch of cycles, decorated, non-decorated, but every non-decorated must be a cycle of length 1. And then you collect all the decorated cycles and then you make a set partition. That's it. That's the configuration that I defined over here. And for X, and the sign of this is defined to be -1 to the number of this. because if you remember, just imagine, just ignore this. Every decorated cycle contributes -1. That means here we have 1, 2, 3. That corresponds to -1. So 1, 1, like that. But that's exactly the cardinality of the set the blocks as a set. Okay. So then, what we want is exactly -1 to n and a sign like this. So our job now is to find the sign reversing evolution, canceling everything that we don't want. Okay, how can we do that? So let's find the sign reversing evolution. Sign reversing evolution phi, like this. So first, so let's say, suppose pi b1 br in the set x. We have a configuration. Imagine this configuration like this in your head. And first, so for instance, the easiest one is like if there is a non-decorated cycle which has always length 1, we can just make it decorated and then create a new block out of it. Okay? So if, how can I say, if there is non-decorated cycle, necessarily the cycle of length 1, it's like this. Or there is a block like J, like consisting of only one element, but everything must be decorated, so it's like that. Then change them. If you have this, replace this by this. If you see something like this, you replace by that. And of course, we have to select I smallest such I. So for instance, in this case, maybe I should give some example. Yeah, let me give you an example that will be helpful. I'm going to explain this with examples, maybe somewhere here. Tau is, okay, yeah, I'm going to 1, 3 star, 2 star, and 4. Yeah. Yeah, that's interesting. So n1 equals 4. The first case is this. First case scenario. Okay. So n2 equals 4 or 5, n3 equals 3, like this. So I created some cycle, now decorated permutation. See, they are decorated, non-decorated, cycle of length 1, so it's fine. So do we see this or this? And yes, we have this, and that's all actually. So this will be cancelled with, sorry, I forgot to create a set partition. 1, 3. Let me write this using a diagram. So pi is like 1, 3, 5, 6, 9. It's one block like this, and 2 star, 11, 12 star, another block like this, 10 star like this. Okay. Yes. And just we have non-decorated cycle. And we also have something like this, but this is smaller. So this will be cancelled with, this will be mapped into, this will mapped into, change this into something like this. So I'm going to erase this, and then instead I'm going to create a block with 4, like that. And if you have a configuration like this, then you would choose 4, and then you will change this into a single thing. But you know this must be inside, must be here, because if you know the integer, you know where it belongs. So this case is the simplest case, the easiest one among the two. So now the second case, no I know this. Oh, let me use the diagram like this. No diagram like this. In this case, find the smallest integer. Find integers ij. Okay, let me find the lexicographically smallest ij, such that I and j in the same block. Okay, let's see. Suppose the same block. Did I define a sign fixed point? Probably not. Okay, let me think about it a little bit. Okay, same block B, same block B, S, and JR. So it must be in the same part from JS, and it must be in the same block. We find 2 integers like that. I think it's easier. I can just give you an example that will be easier. Pi tau equals 1, 3, 4, 2, union 5, 6, 9, 7, 8, union 10, 11, 12 star. And tau pi is like, I'm gonna collect 1, 3, 4, 2, 5, 6, 9 in one block, and 7, 8, 10 the second block, and 11, 12 in the third block. Okay, yeah. So we find ij, smallest ij, such that ij are in the same block and also in the same part. In this case, ij equals 1, 2. Because 1, 2 is in the same block and also from the same set. Okay, same homogeneous numbers if you want. Then this, this is a permutation. If you consider only those elements in the same block, they form some kind of permutation. So in this case, multiply 1, 2 to this elements. 2. So in other words, 1, 2 multiplied to, as a permutation, we can combine them. And this, as a permutation, 1 goes to 3, 3 goes to 3 goes to 4, and 4 goes to 1, and 1 goes to 2, so 4 goes to 2, and 2 goes to 1. So this is a permutation that you can get if you multiply this. That means we're gonna combine these two together to get a single cycle. So that means I'm gonna map this with, maybe I can make it a little smaller. Like this. So this will be mapped with this, where I'm gonna replace this by a new cycle. So the idea is we change the number of cycles basically by because if you can multiply a transposition ij, you will always change the number of cycles, decorated cycles. Because either merge two cycles or split one cycle into two. So if you have the same map here, you will still have to choose I and j, the same ij. You multiply ij, then you will get back these two cycles separated. So that's basically the idea. And this is the sign reversing involution. And what are the fixed points? Every block must have, how can I say, did I write it down here? Yeah, I think I'm running out of time, so fixed point means that first, BI has cycles decorated, cycles of length 1, and also size must be greater than or equal to 2, because if the size is 1, then it will be cancelled in the step 1. And BIJJ has at most one element for all j. So if you combine all of this, you will get the exact description that we have over here. Where is it? Yes. Yeah, but yeah, because of the time limit, I'm skipping the details, but yeah, that's basically the proof. Okay, then I stop here. Thank you for your attention.